Hi, and welcome to Allen High School's discussion of chemical bonding at the APIB level. And we're working on Lewis dot structures and ultimately moving into some of our models for the three-dimensional shape of simple inorganic substances. We're going to combine our knowledge of ionic and covalent Lewis dot structures. Recall that strontium in group 2 has 2 valence electrons. So metals are losers. It's going to lose those 2 electrons to become a 2+. Now we also drew the phosphate. There's 3 strontiums and 2 phosphates. So I'm going to start my drawing with my strontium. That's ionic between. Within the phosphate, we did this one earlier, and remember we're drawing really a simplified phosphate. Phosphate does something, and frankly sulfate, does something a little unexpected. If you did a quick image search of those, you would see that they double bond when you wouldn't necessarily predict the need for double bonding. There's no deficiency of the central atom. So then I put a 3-. Now, these are covalent bonds within, so that's a covalent bond, and it's an ionic bond between the two. So we see both types of bonding present here. And then we will alternate. There's the strontium and another phosphate. I'm going to get a little sloppy to do this quick because you don't need to see me do these little dots everywhere. There we go. That's one of the sloppiest phosphates I've seen in a long while. Sorry about that. And then strontium 2+. Okay? So there's 3 strontiums and a phosphate. This tells us nothing of three-dimensional shape. We're not doing crystal structures for ionic compounds. Now, let's get into something that's pretty interesting. We're going to talk about 2 scenarios in which it would be reasonable to draw more than one Lewis dot structure. Scenario 1 you saw in pre-AP chemistry, and you should have seen if you were on grade level chemistry or general chemistry as well. Now, to resonate means to match energy, or if you think of stringed instruments, for example, strings can resonate, vibrations and higher harmonics can occur as we match vibrations or energy. So to resonate means to match energy. Now, note here, this is so very important. There are teachers who teach it this way, and that is an incorrect way. The molecule doesn't flip-flop back and forth from one to the other. The actual, you might describe as a blend or a hybrid or an average of the resonant. It's not a flip-flopping back and forth. The shared electrons are said to be delocalized. Remember when we talked about sorry, I can't write and talk at the same time. Delocalized. Sorry. Try again. Oh, Dina. There we go. Talking and writing at the same time. Remember, delocalized electrons were able to move around amongst the structure, and that's what we see here. There ends up being a bigger playground, so to speak, for the electrons. Now, we're going to be discussing this term bond order. It's a little bit of a simplified view of bond order, but it's going to be the number of bonds, the number of electron pairs, divided by the peripheral atoms that are doing the sharing. So if we did, let me draw this a little bigger than what that picture ended up being. Okay, let me draw it the same way that we had it. Notice that we have one with the double bond on one side, or we could have drawn the double bond on the other side. Now, where that double bond ended up would have solely depended upon where you started distributing the electrons. There's no difference in these two. These are equal energy. The actual is a mixture or a hybrid. it's not a flip-flop back and forth. It's a hybrid. So instead of being 2 bonds and 1 bond, these extra electrons are delocalized or spread out. And so we end up with, let me draw these as bonds instead. Whoa, I really lost that there. Let me draw this bigger as bonds instead. We'd have a full bond, and it's common to write the delocalized bond, that shared bond, as a dotted line to indicate that the electrons don't spend 100% of their time there. So what we have is a total of 3 bonds, right? 1, 2, 3. Either way we counted, it was 3 bonds. There are 2 peripheral atoms, so we would say that this has a bond order of 1.5. Now there was a non-bonded pair on that central atom, so we're going to call this an AB2X structure. We only count peripheral atoms. We're not worried about how many bonds are in between. We're just counting how many atoms, or this could be a group of atoms, hanging off a center. So that would be called an AB2X structure. Now, I want you to note we need to get a little bit into function here. We're going to talk a lot more about function in the next chapter. This is actually chapter 5, and in chapter 6, we'll talk about function in a little bit more detail. But this is an important thing that occurs with bond order. As bond order increases, we have more electron density between 2 atoms. That draws the 2 atoms together, so bond energy decreases, bond length, I misspoke. Bond length decreases and bond energy increases. It's like putting a stronger magnet. So as we increase bond order, we decrease bond length, and we increase bond energy. And you need to know this inside and out. And I tried to make a little bit of a humor out of it to help you understand that a little bit better. But I want you to make sure that you understand that concept. And if you don't, that would be a prime thing to ask me in class. All right, let's do one. See what we come up with. We have the carbonate ion, carbonate CO3 2-. If you don't know your polyatomic ions, you are definitely, I'll let you ponder that one. COOO, I've got 4 valence electrons from the carbon, plus 3 times 6 from the oxygens, plus 2 extras, that gives me 24 electrons. So I would make my bonds. Let's make those dots a little bigger. Make my bonds. I like to satisfy my central. I've used 8 electrons, so I have 16 left. 2, 4, 6, 8, 10, 12, 14, 16. So I've used up all 16 electrons, but there's a problem. One of my oxygens is not satisfied. It does not have the full octet. So remember what I said, look to mama for extras. Now, I'm going to look to mama, if I can have something of an eraser here. So I'm going to, my eraser quit working on me there. Make it a little bigger, I guess. There we go. Lost my carbon in the process. Yay, Mimeo. There we go. All right. Now, we can't just move those 2 electrons over because now the carbon's not satisfied, right? And if mama goes hungry, then there's a real problem because mama can't take care of everybody. So mama will share, let me make those in a different color, share those 2 electrons. Now, it's an ion, so we still need our brackets and our charge. And this would be an AB3 structure. Now, here's where resonance comes into play. It was totally random where I started and where that double bond ended up. There's no reason why the double bond couldn't have been on that oxygen. Or, for that matter, the double bond could have been on this oxygen. And what that means is that we have equal energy, we have resonance. And the actual is a blend of these. Now I'm going to have to erase to give us a little bit of room, but that's okay because it doesn't exist as flip-flopping amongst those. It's not an equilibrium amongst structures. It's an in-between. And I'm just going to do the skeleton Lewis dot for now. I think that'll make my point. Each oxygen had one bond, and then we had that pair, that extra pair that was delocalized. Okay, and you'd have to fill in the rest of the little oxygen or the electrons around that. Okay? Now, what that means is I had 4 bonds divided amongst 3 peripheral atoms. So I have a bond order of 1 1/3. So that's how we calculate that. Okay, the next one, the next video is going to be a little trickier. Yeah, covalent is the longest. We're going to talk about our second scenario where they're not equal energy. So until then, this is signing off.